Ever wonder what really happens in that split second after you hit search on Google? It feels like magic, but it's actually a massive orchestra of thousands of computers all working together. But what happens when just one of those instruments is out of tune? Today, we're pulling back the curtain on Dapper, Google's incredible system for finding that single tiny error in a sea of a billion requests. All right, so to really get why Dapper is so brilliant, you first have to understand the sheer, mind-boggling scale of the problem it was designed to solve. We are talking about a challenge of truly epic proportions. You know, it all starts with something you and I do dozens of times a day, without even thinking about it. You type something in that little search box, you hit enter, and poof, you get results. But behind that screen, a whole hidden world just sprang into action. Yeah, that one click doesn't just go to one server. Oh no, it sets off a digital cascade, a waterfall of requests that bounce between thousands of different services. You've got ad systems, spell checkers, image processors, each one doing its tiny little job to build the page you see in a blink of an eye. Now, just imagine for a second that one of those thousands of little services has a hiccup. Maybe it's a little slow or it throws an error. The whole request can fail. For a Google engineer trying to find that one faulty link in that colossal chain, well, it's like trying to find a needle in a digital haystack the size of a continent. That's the problem.
So with a problem that huge, where do you even start? Let's put on our system design hats for a minute. If we were building the perfect tool to fix this, what would our absolute must-haves be? As you're about to see, the wish list is pretty demanding.
Okay, first and foremost, the absolute #1 rule. It can't slow anything down. I mean, can you imagine if the tool meant to monitor Google search actually made your searches slower? Yeah, nobody would use it. On top of that, it has to be super easy for every single engineer to use. It has to work on every service, be on 24/7, and give you data almost instantly. That is a really, really tough balancing act. And, oh yeah, one more tiny thing. The system has to handle a truly massive amount of data. We're talking about processing 1 terabyte of trace data every single day. Just think about that. It's a staggering amount of information to collect and make searchable. So how on earth did Google's engineers solve this puzzle? Well, it all comes down to 2 surprisingly simple but incredibly powerful ideas that are the heart and soul of Dapper. Let's break them down. The first core concept is something called a span. The best way to think of it is like a single breadcrumb dropped along the request's path. Every time the request does one specific thing, like call a database, it drops a breadcrumb. And here's the key. Each breadcrumb knows which one was dropped right before it. It has a parent ID. By linking these parents and children, you start to build a chain. So you can see here, the profile check kicks things off. And when it calls the blacklist check, that new span knows its parent. You're basically building a little family tree that shows exactly how one operation led to the next. You're following the breadcrumbs. So if a span is just one breadcrumb, then a trace is the entire trail. It's the complete story of one user's request, made by stitching together all the breadcrumbs that share the same original ID. By following that trail, engineers can see the whole journey, from that first click all the way to the final result. Okay, so you're probably thinking, a system that tracks billions of requests must be insanely complex under the hood, right? Actually, no. And that's the real beauty of Dapper. Its architecture is an absolute masterclass in keeping things simple. Let's see how it works. It's really just a 3-step dance. Step 1, the application just writes the trace info to a plain old log file on its local machine. Nothing fancy. Step 2, a little background process on each machine just scoops up those logs. And finally, step 3, central servers pull all that data, put it together into the spans and traces we talked about, and store it all in Google's giant Bigtable database. That's it. Simple, tough, and it just works. And you know what? This simple system is crazy fast. From the moment something happens to the moment an engineer can actually look at its trace, we're often talking less than a minute. When you're trying to debug a live fire, that kind of speed is an absolute game changer. This all sounds great, but we've kind of been dancing around the elephant in the room. That #1 non-negotiable rule. How does Dapper do all this without slowing Google down? Well, the answer is the secret sauce that makes this whole thing possible. Seriously, let's think about it. How can you possibly log every single step of a request across thousands of machines, generating a terabyte of data a day without causing any noticeable slowdown? It seems impossible, right? The answer is one brilliantly clever trade-off. They don't trace every single request. They sample. And when I say sample, I mean they really sample. In production, Dapper's sampling rate is incredibly low. It only traces about 1 in every 1,024 requests. You might think, how is that enough? But at Google's scale, that tiny fraction is more than enough data to spot patterns and find errors, all with basically zero impact on live systems. It's just genius. And the system is really smart about how it samples. For a massive service like search, it uses a fixed rate, kind of like taking a picture of every thousandth car on a busy highway. But for a smaller service with less traffic, it switches to adaptive sampling. This makes sure it still gets, say, at least one picture every minute, so nothing important ever gets completely missed. So what can we all learn from this amazing piece of engineering? Because Dapper is so much more than just a tool. It's a genuine masterclass in how to think about designing systems. The lessons here are just timeless. First, simplicity wins. Complex problems don't always need super complex solutions. Second, don't reinvent the wheel. Leverage the powerful tools you already have. Third, embrace clever trade-offs. That sampling idea was the key that unlocked an impossible problem. And finally, and maybe most importantly, focus on your users. A tool is useless if no one actually uses it. In fact, these exact principles are now the foundation for modern tools like Jaeger and Zipkin that engineers use every day. This quote from the original paper just sums it up perfectly. By building on top of the infrastructure they already had, the Dapper team created a system that was way more robust and scalable than if they'd tried to build every single piece from the ground up. And that really leaves us with a final thought. Dapper's genius wasn't in adding more complexity. It was in being clever enough to take something away. It really makes you think, doesn't it? In the systems we all build, what's the one impossible problem that could be solved with just one clever trade-off?